Hi everyone, I'm Amit as introduced. So I would like to thank the organizers to give me opportunity to talk here. The title of the talk is Environmental Effects in Galaxy Cluster. So talking about galaxy clusters, as you know, it is a collection of hundreds to thousands of galaxies. And at the center of a typical galaxy cluster, you find a bright big galaxy, and the rest of the galaxies in the cluster are known as the satellite galaxies. There are various processes going on in the galaxy clusters, because of which the evolution of the satellite galaxies which are residing there can be affected. What are the processes like? Processes like tidal stripping, because of which the mass from the satellite galaxy, mainly from the outskirts, can get stripped. There are other processes like galaxy harassment, in which a spiral galaxy may turn into a elliptical galaxy because of multiple encounters. What we are interested in how this cluster environment is affecting the dark matter distribution around these satellite galaxies. So how do we answer this question? Is we use a technique called weak gravitational lensing. Why? Because it gives you the total mass of the satellite or total mass of the object. As introduced, as this technique is already introduced by the earlier speaker Somnath in the morning, I would skip over this by saying just one line that in weak gravitational lensing, you measure the distortions caused by the intervening matter on the images of the background source galaxies. So, and these distortions give you a information of the mass of this intervening matter, which act as a lens here. Okay, since you want to do lensing, you need something to act as lens and something to as a source. So, and I said that these distortions on the image of background galaxies give you the information of mass, and you are interested in understanding how the mass around satellite galaxies is affected. So you use the satellite galaxies as a lens galaxies. From where do you get these satellite galaxies? We select these galaxies from one of the cluster finding algorithm, which is RedMapper. And what are the source galaxies for us on which the distortions are imprinted? Are the galaxies from year 1 data of hypersonic prime chemistry. Okay. So our question was that how the dark matter distribution is affected. So the good way to answer this question will be, you create a sample of galaxies which is very similar to your satellite galaxies, but this sample don't live in a cluster environment. So, and you are creating this sample similar to satellites in stellar masses, stellar properties. So in this way, if you measure the mass around these two samples, and if there is some mass difference between these two samples, it is primarily in dark mass and due to the environment, because one of the sample is residing there and what is not affected by those processes. So we create that sample, we find galaxies in the non-cluster environment which match to our satellites in photometric magnitudes, UGRIZ. Matching galaxies in photometric magnitudes, make sure they match in colors also. Hence, we make sure that statistically our galaxies in which are not in cluster, which I am saying the control galaxy, and our satellites has similar photometric and redshift estimates. Okay, so having the sample, let's go ahead and see how the signal look like around these galaxies. When I say signal, I am talking about delta sigma, which is related to these distortions in the shape which are directly observable, and this delta sigma is can be modeled and defined with this equation as a difference of two quantities. How to understand these two quantities is in order to understand these two quantities, let's create a circle of radius r around the galaxy. You are seeing something in the pinkish region. So the projected mass density within this region is the first term of the equation, and the yellow is projected mass density in the annular region is the second term of the equation. So and you understand that this is modeling and this is directly related to the observations which are characterized by this quantity gamma t. Okay, how the signal look like around the galaxies which are not in the cluster. This is how the signal look like. This is monotonically signal, decreasing signal. Okay, so how the signal look like for satellite galaxies? It is a combination of three type of mass densities there. So see, mass around a satellite is its stellar mass, its dark mass, and there is some of the mass from the parent galaxy also, in whose influence it is evolving. Okay, so these three terms characterize each of these. Baryonic is the stellar mass of the galaxy, satellite galaxy. Subhalo is the dark matter gas, and the cluster is due to the mass of the BCG. Okay, so how the signal look like for these satellites? So here I am showing you the signal as a function of distance from the center of the satellite galaxy, and these three terms dominate at different distances from the satellite center. Like at these distances, it's the first term, which is the stellar mass of the satellite dominate. As you move ahead, here the subhalo mass of the satellite dominate, and here the mass of the parent BCG dominate. Okay, this is how the qualitatively signal look like for one satellite central pair. There are many central satellite galaxies there in the galaxy cluster environment. So the total signal is the average of all of them. So here I am showing you a signal for the satellites which are having a separation of 0.1 to 0.3 megaparsec, H inverse megaparsec from the cluster center. And you see the signal in green stars with error bars is qualitatively looking like what I showed you in the previous slide. Okay, you have the signal, you model it with assuming some density profile, which is NFW here, and here this model has some free parameter which characterize the mass of the satellite, and you ask that whether the mass of the satellite is same as that of the other sample which we created, which was matching to our satellites in stellar aspects. So we measure the signal around that sample, and this is how the signal around that sample look like, which I am showing in the reds. You are seeing the signal in red, which is for non-cluster galaxies, is consistently above the signal from the satellite galaxies. And I told you that this delta sigma gives you information of the mass of the object. So you can say that the mass of these non-cluster galaxies, which are shown in red, is higher in comparison to the mass of the satellite galaxy. Now we ask a question: if the separation between separation of the satellite increase from the cluster center, what happens? Do we see the same kind of mass difference between these isolated galaxies and the satellite galaxies? We repeat this exercise for the satellites having different separation from the cluster center, in as shown in the different panels. For the satellites having separation indicated above the figure, and you see that as the separation of the satellite increases from the cluster center, the mass difference decreases and satellites start behaving like field galaxies, non-cluster galaxies. Okay, so this can happen because of two reasons. One is we can say that the stellar to halo mass relation followed by the satellites and these non-cluster galaxies are different. Other is invoking some kind of galaxies which are known orphan galaxies. I will talk about this one by one. Okay, so here I am showing you a posterior distribution of the mass histogram for these control galaxies which are not from the cluster and satellite galaxies in red versus green. So you are seeing that if you talk about the first panel, which is upper left, you see that there is some mass difference between these satellites and these non-cluster galaxies. And as you are moving far means the as the separation of the satellites is increasing from the cluster center, these mass differences between these two samples are nulling out. Okay, are starts looking similar. So okay, this is we also ask a question: is there some dependence of subhalo mass on the distance from the cluster center? We don't find such strong dependence. Okay, so another case I said that is invoking orphan fraction. What do I mean by that? Orphan are the galaxies, a particular kind of galaxies which have lost most of their dark matter mass, mainly due to multiple pericentric passages. So now you are saying that your satellite sample consists of very extreme kind of galaxies. One is the kind of galaxies which are exactly like fields. One are these orphan galaxies which have lost all of their mass. Now I'm saying that if you try to count the mass difference which you observed earlier by this sample only, you can put a upper limit on the admissible value on these orphan galaxies which are possible from observations. So you expect that these orphan galaxies should decrease in population as the separation of these galaxies, as the separation of the satellite increases from the cluster center. So that we also see in the observations. Here I am showing you that data with the blue dots and error bars. What I'm showing in the yellow arrow is, so these cluster catalog from where I have taken the satellite galaxy are affected due to the contamination from the non-cluster galaxies. Okay, so so we account for those galaxies and we saw how this orphan fraction shift because of these interloper galaxies contamination due to this galaxy. I think I should stop here. I can't go ahead, and I would leave you the semester.
Thank you, Amit. Yeah, questions?
Thanks, Amit, for the nice talk. So I'm a little confused. So do we need orphans that to model it that have lost all their mass, or some amount of tidal stripping can also explain?
We are putting an extreme limit on this by doing this, by considering the satellite sample of this kind. Otherwise, yeah, there are satellites, means normally satellites are like which lose mass.
Right. So that could
we
also
are considering the extreme scenario so that we can put this upper limit on this.
All right. Okay.
Any other questions?
Okay, I think you, very nice result. I think you said this early in the talk, but I just wanted to ask, to what extent do you match the masses or the photometry or stellar masses, I guess, of the comparison sample in the cluster
these
galaxies?
stellar masses are not not given from the catalog. We are just matching. I am showing you how well they match. You can see that the histograms are nearly overlapping for this control sample and the satellite. So you can say that these are matching quite well.
In the subhalos in dark matter halos. So the subhalos in parent dark matter halos, they have a distribution of masses.
Distribution of dissipation of masses. Yeah. So okay.
And this distribution, it could depend on distance from the center of the.
Yeah,
halo,
we can't.
Whereas this
with the observations, we can't comment on. Like it is a combination of all the effects in the cluster.
Okay.
It is we can't distinguish.
Thanks.
Okay, so let's thank the speaker.